Hey everybody, let's go over problem number 3 from this packet so we can practice some stoichiometry. And the first thing that we need to do for this with tungsten 3 oxide decomposing into its elements is we need to figure out what the formula is, because we need to make sure we can write a chemical equation. So this is going to be tungsten is W, and then the charge on tungsten, remember, is that number in parentheses because it's a transition metal, and then we go O, and oxygen is a 2 minus. So we look at that, we see what the least common multiple is. The least common multiple is 6, so we need 2 and 3. So the formula for tungsten 3 oxide is W2O3. Now typically we wouldn't necessarily know what it decomposes into, because it can decompose into a million different things. But in this case, the reaction, or the question, tells us that it decomposes into its elements. So what happens is this decomposes into tungsten, and remember, tungsten is a solid, it's a metal, plus oxygen, O2, oxygen is a gas. Okay, the only other thing that we need to do is figure out what state this guy is in. And so this is an ionic compound, the strongest intermolecular forces, so the guess is that that is a solid. Now, that includes states, but now we need to make sure we balance this. I'm going to balance this guy in blue. Okay, and now we look at the coefficients here. So here, there's 2 of these and only 1 of these, so I'm going to put a 2 there. Okay, now the second, for oxygen, we have 3 and we have 2, so we need 1.5 of these things. Now the problem with that is that we cannot have halves in our balanced chemical equation. We can only have that in one specific type of chemical equation that we could learn later on. But when we see a half, we can't do anything. So we're going to take all of this reaction and multiply it by 2. So the balanced chemical equation is W2O3 solid reacts to form 2W, multiply by 2, everything gets multiplied by 2, solid, plus 3O2 gas. So there's our balanced chemical equation. Okay, so we got that. And it says, determine how much of each product is made in moles. So if we're trying to determine how much product is made in moles, we probably need to do an ICE chart. So we're going to do an ICE chart here for this. Okay, and so we're going to label ICE. And now, this, we need to know how much, so it's let's see, so this is 0.827 grams. Okay, so remember, the ICE chart only uses moles in here. So let's take this and do some work, because what we're going to have to do is convert to moles in order to get that value in here. And again, I don't know why my pen is doing that. That's weird. So let's do a little work. In order to convert to moles, okay, in order to convert to moles, we need the molar mass. Grams of W2O3. X line, we convert using the X line. So we're going to put grams on the bottom, moles on the top, and now we need the molar mass, the value that goes in there. So tungsten is equal to 2 times, and now I have the periodic table here, so the molar mass of tungsten is 183.84. Okay, so that's times 183 point, let me make sure that that's readable. I don't know what the heck is going on right now. Okay, so times 183.84, and then oxygen is equal to 3 times 16. Okay, so now the molar mass of that is, we'll do 2 times 183.84 plus 3 times 16, and we get that, and we get 415.68. So this is 1 and then 415.68. Now we do some math. Again, we have to figure out how many moles this is. So we do 0.827 divided by 415.68. Okay, and so now this is a really tiny number, 0.0019. Now I'm going to round it to 3 sig figs, so that's moles of W2O3. Now we have an answer there, so this is going to be 0.00199 moles. Okay, now that's the start. How much of these do we have to begin with? We don't have any. The reason why we don't have any is because it's not mentioned in the reaction, so we're going to, or in the problem, so we're going to start with 0 there. And then this is a 0 here because we're going to use all of this up. So the amount by which this changes is 0.00199. Okay? Now, once we have this first change box here, once we have this first number, we can now calculate all the other values of every change box. So we're going to go down, and again, we're going to calculate all the values of the change box. So we're going to go here, we're going to go 0.00199 moles of W2O3. And now, instead of trying to get rid of moles, we want to get rid of W2O3 and convert it to W, to tungsten. Okay? And so we use the balanced chemical equation. Whenever we're going across the ICE chart, we use the balanced chemical equation. And so now this is a 2 and this is a 4. Okay? So we do the math. Now if you see the pattern there, that's cool. If you see the math, I'm not necessarily, to show the work. You don't have to necessarily show the work if you can see what the answer is. Okay, but I'll show it to you. So it's 0.00199 times 4 divided by 2. Some of you may have been able to see that 4 over 2 is 2, and then you could multiply. But if you didn't, there it is. So it's 0.0398. So we come up here. So this is 0.00398 moles. And now we're going to do this same thing for oxygen. So here we're going to go 0.00199. This is strange-a-rooney. Okay, 0.00199 moles of W2O3 times, and then we're going to put W2O3 on the bottom and then O2 on the top. And we use the balanced chemical equation, so we have 2 of those and 3 of those, right? As I scroll up, 2 and 3. Okay, it's hard to see because the calculator is in the way. Okay, so now we can do that math, and we get 0.00199 times 3 divided by 2, and we get, again, we have to round to 3 significant figures. Oops. So this is 0.00299, and again, some of you may have been able to see that, others maybe not, but either way, we get the answer here. Okay. And so now keep in mind that we are making products, so we're going to add that to however much we started with. So this is 0.00398. 0 plus that is 0.00299. And there's our answer. But notice that it asks how much is made not only in moles, which we just did, but now in grams. Okay, so now we have to convert to grams. How do we convert to grams? We use the molar mass. So it's a good thing we looked up molar masses. So I'm going to get a new little section here, and my double line indicates a section break. Okay, so we have 0. I'm going to extend the page a little bit. 0.00399 moles of W. And we're going to X-line that. We're going to do moles on the bottom, grams on the top. And when we look at tungsten is 183.84. We looked that up already. So 183.84 per 1 mole, and that's going to equal, let's see, 0.00398 times 183.84, and we get an answer of 0.732 grams. So I'm going to take that, and I'm going to put that up here. Okay, and that's 0.732 grams. Now, do it again because we have for O2, but keep in mind that O2 here is, do it in black, 0.00299 moles of O2. X-line, moles on the bottom, grams on the top. For every 1 mole of here, now we have O2 because oxygen is diatomic. So that's going to be 32 grams per mole. Okay, so we have 0.00299 times 32. And so this is equal to 0.0957 grams. Okay, so now we're going to go up here. And now we get, here, it's 0.0957 grams. Now I'm going to double check here. Okay, I'm going to do that in red. And because what I know is the law of conservation of matter says however much we start with in grams, we should end with. So I'm going to add up all the starting grams, and in this case it's 0.827 plus 0 plus 0, so that's 0.827, and I'm going to add these two together, so it's 0.732 plus 0.0957, and we get 0.828. Close enough. So I know that I did this pretty good. Okay, little rounding probably. If I were to carry out all my calculations to 1,000,000 significant figures, I'd probably get right on. But we round in chemistry and we get close enough, and that's close enough to say, yep, I'm good. So there's that question. Have a great day.